Hi everyone. So today we're going to talk about the pretest-posttest design, also known as a repeated measures or dependent measures design. So obviously when you're doing research, you have to decide what kind of design you're going to use, right? The first thing you have to think about is, do you want to do a repeated measures design or just a post-test design? So some of the advantages of doing a pre-test post-test design would be that you actually compare the same individual at two different times. So this would be most beneficial if you're actually doing your study on something that might actually differ from person to person. So something that has maybe to do with their personality or coping mechanism, or a cognitive variable would be a really good example. But we all have different cognitive abilities. If you're looking at reading comprehension skill or working memory capacity, all those things differ slightly from person to person. So it's advantageous that you're actually using the same person at two different times, because you don't end up comparing apples with oranges. You actually compare the same person to themselves at two different times. One time prior to the intervention, and then one time after the intervention was introduced. So some of the benefits of conducting a pre-test post-test design would of course be that you actually obtain two measures from the same participant at two different times. So you don't have to worry about any selection differences between your groups. Even if somebody actually drops out earlier, right, you still have that pre-test measure. You can maybe look at if there's something that people who drop out have in common. Maybe they're different from the people that actually stay in the study. Another benefit is also that you actually need fewer participants because you're getting two data points from each person. And that, of course, gives you more statistical power to detect an effect if there is one. And again, individual differences are not a problem because you don't end up comparing two different individuals under two different conditions. You actually know that you're comparing the same person one time prior to the intervention and one time after the intervention was introduced. But just with anything, there's also some disadvantages of using the pre-test post-test design. Some of them, of course, would be that sometimes it's simply not possible, right, to do a pre-test post-test design, because once maybe somebody has been exposed to the study, they might actually have a better understanding of what your hypothesis is. So you've already given away what kind of the goal of your study is. It's also possible that if it's something like involving drugs, or if you're doing animal research, lesioning a part of the brain, right, you can't reverse that. So sometimes it's simply not possible to do a repeated measures design because you can't actually expose a person or an animal to one condition twice. Another reason why sometimes people shy away from using a pre-test post-test design would be carryover effects, also sometimes referred to as order effects. So there might be something about the first exposure that maybe changes your behavior the second time around. So take, for instance, maybe the first time you took the SATs, right? It was completely new. You didn't know what to expect. And as a result, maybe you did poor on the first test that you ever did compared to any subsequent tests. So that might also be true about a study, right? If you're giving people, a new task that they've never done before, such as a word puzzle or, a similar task, they might just not have known what to expect. So they naturally do better the second time around. If that might be an issue for your study or your research question, maybe the pre-test post-test design might not be the best test. But there's also ways that we can account for some of those order effects. So other reasons for why we might see order effects might be the one that I already mentioned, right? People get better over time, so you get a better hang of the task. So practice and learning might actually lead to better scores the second time around. Another issue with a pre-test post-test design might be that the participant just gets tired of being in the study. Maybe if they have to be there for a long time, they might just overall get tired, or they might just get tired of doing this particular task. And then last but not least, of course, there's always the risk that people actually will gain a better understanding of what you're actually doing. So they pick up on what your hypothesis is, and then the risk is always that they might actually change their behavior to either go against what they think your hypothesis is or maybe to support it. So you want to, if possible, avoid that. So obviously there's a lot of advantages to doing a pre-test, post-test design. And as a result, right, there are ways that we can actually handle some of those order effects that I've been talking about. So let's take a look at how we might actually handle them. So let's suppose that you want to do a study where you present people with targets on a computer screen and you want them to respond to the targets on the screen in a certain way. But you want to test if the kind of breakfast that you have actually matters. So you may have heard, the debate between different breakfasts, right? Maybe one is better than the other and maybe increasing your performance. So the research question that we have here is, does it actually matter if you have Rice Krispies or Wheaties for breakfast? So we might want to see if the kind of breakfast that you have will have an influence on how well you perform on this cognitive task that measures your response time on a computer screen reacting to different targets. So in this case, right, dealing with the order effects is definitely possible, right? Sometimes, as I explained on the previous slide, it's not really possible, but in this case, right, I definitely think that would be possible because there are probably only modest changes that we would have as a result of practice. So what we could do is actually, here you see in the graph here, and on the x-axis you see the number of sessions. So session 1 maybe performed on one day, you had Rice Krispies for breakfast, and that was the first time you performed the task, and your average reaction time responding to the targets was 1,200 milliseconds. The second day, when you had Wheaties, your reaction time was actually much faster. It only took you 600 milliseconds to respond to the targets on average. So you might say, well, clearly Wheaties is much better, but it's also possible that the improved performance is actually due to a practice effect. So to handle this order effect, right, we might actually consider doing a different design than just, having one day with Rice Krispies and one day with Wheaties, because we want to make sure that this effect that we're seeing, the improvement with Wheaties, is not due to simply a practice effect, which is quite possible, right? So how do we do this? So as you can see, right now I have a slide up for the Swedish band ABBA, and you can also hear the song, right? And you might wonder, what on earth does ABBA have to do with research methods? So this is kind of my way of telling you that the way that you can handle simple order effects is using the design ABBA, also referred to as ABBA in research methods. So how do we do this? Okay, so let me kind of orient you to what you're looking at here. So we're still doing the experiment with the Wheaties and Rice Krispies, but instead of actually just exposing each participant to Wheaties and Rice Krispies on one day, we actually have 4 individual sessions. So what we do here is we want to make sure that the improvement that we saw with the Wheaties isn't just due to a practice effect. So what we can do is on the first time that the participant comes into the lab, we give them Rice Krispies and they perform the cognitive task. And as you can see, right, they're performing the worst, right? It takes them the longest, probably because they've never seen the task. They're just getting used to it. On the second day, we're introducing Wheaties, right, the different kind of cereal, and that's really what we're interested in. That's what we want to see, if that actually changes your performance. So as you can see, people do actually slightly better on average, right? So only 1,000 milliseconds. And then we're going to, on the third day, again do the Wheaties condition, and yet again they're doing even better, right? So there's kind of this continuous improvement, probably just due to practice. So they're only taking 800 milliseconds. And then on the last day, where we would expect people to do the best because, right, they have done this 3 times. This is old news. They're really good at this task. So on that day, as you can see, they're actually performing the best, right? It only takes them 600 milliseconds on average to respond to this task. So this is assuming that really our intervention, right, the Rice Krispies versus Wheaties, has no effect, right? We're purely looking at a practice effect. But this is showing quite nicely how actually these numbers average out, because if you look at it, right, if you take the Rice Krispie condition, so the 1200 and 600 milliseconds, so day 1 and day 4, right, it averages out to about 900 milliseconds. And then if we take the Wheaties condition, which occurred on day 2 and 3, if you're averaging out those two numbers, you're also getting about a 900 millisecond average. So this means that we would be accounting for our practice effect. Okay, so this is also called within subject counterbalancing because each person here would have to go through all 4 sessions and experience all 4 sessions. So we could actually do complete counterbalancing within subjects. So this is one great way that we could actually handle this order effect. Now, let's just compare our awesome ABBA design to, if we were to do something like ABAB. Let's see if maybe that's also possible. So as you can see here, we basically flip the days, switching it each day. So on the first day, you get Rice Krispies, then Wheaties, then again Rice Krispies, and then again Wheaties. So let's see if those numbers actually pan out. As you can see, right, if we actually take the averages of day 1 and 3, for the Rice Krispie condition, condition A, which is marked in yellow here, it does not come out to be 900 milliseconds, right? It actually comes out to be 1,000 milliseconds. If you compare that to the Wheaties condition, right, which was done on day 2 and 4, now that actually comes out to be 800 milliseconds on average. So those two are not the same anymore. And again, right, we're just looking at the practice effect. We're assuming that Rice Krispies and Wheaties would make no difference in this case. Right, so ABAB does not work out, whereas ABBA, right, ABBA actually did work out to be equal. So that would be the desirable design to use if you want to make sure that you're actually accounting for a small practice effect that you would see with a similar cognitive task like this one. Okay, but there's another challenge, right? Sometimes it's not just a practice effect that we actually see, but there might also be a fatigue effect, as I mentioned on an earlier slide. So people might actually just get tired of either doing the same task over and over again, they get bored, or if it's all done in the same day, they might just get tired of being in the lab doing the same task over and over again. So as it turns out, ABBA works really well for a linear pattern of a practice effect, but it does not work very well for nonlinear patterns. So as you can see here, right, if there is something nonlinear going on where at first you get better and better and better at a task, but then you actually get worse again because you just get tired of the whole thing. Right now, our numbers do not come out the same again, as you can see right here. So if we do ABBA, and there's a practice effect in addition to a fatigue effect. So, right, this is no longer linear. It doesn't just continue getting better, but rather it gets better and then it actually gets worse again, as you can see with the last condition. Right, there's another confound that we introduced because it does not equal out to be the same for the two conditions. So if you're suspecting that you're going to have both a practice and a fatigue effect, probably ABBA, as sad as it is not going to work out. So you have to actually look for other options. So as you can see right here, if you do, basically the question now is like, what do we do now, since we know that ABBA does not work out and we already know that ABAB didn't work out. So we have to find a different solution to the problem. So if you want to look right here, there's two examples here. So if you do, instead of actually doing complete counterbalancing, you can also do something that actually is done between subjects rather than within subjects. So the counterbalancing is done across subjects, meaning that not each person sees every single condition. Okay, so you could have one person, for instance, doing first Rice Krispies on day 1, and then Rice Krispies on day 2, and then Wheaties on day 3 and 4. So if you then have a practice and a fatigue effect, right, it would be kind of skewed one way, but then you have another individual, right, another subject altogether, actually experiencing the same conditions, but experiencing those same conditions in a different order. So now they see Wheaties first on day 1 and 2, and then day 3 and 4, they see Rice Krispies. So things are flipped. So in that way, right, you're actually counterbalancing across subjects, not within subjects, because each person sees the same conditions, but they all see them in a different order. So that's another way that you can actually handle this. So this is an example of complete counterbalancing. So as you can see, this actually works quite well for a nonlinear order effect where you have a practice effect and a fatigue effect. So right in this example here, again, the numbers work out to be the same. So this is very promising and might actually work for this example where you only have 2 conditions. What's problematic is that the more conditions you have, the more actually orders you have to complete. So, it's possible to do this with 2 conditions. It's even possible maybe to do it with 3 conditions. As you can see at the bottom here, it says the way you can calculate all the possible permutations is if you have 3 conditions, you can just take 3 factorial. So it's 3 times 2 times 1. So that's 6, and that's still manageable. It's a lot, but there's actually 6 different orders. So you would have to make sure that you get a lot of subjects so you can put all of them through in one of those 6 orders, but you would have to make sure that you have, at least probably 10 in each of the orders. So that's a pretty substantial number of subjects that you would need. So in this case, right, you would do complete counterbalancing where subject 1 comes in and then they see the study in the order of A, B, C. So right, we have A, we said was Rice Krispies, B was Wheaties, and let's say C was oatmeal. So they would see it A, B, C. And then the next person that comes in the lab sees it in a different order. So they first see Rice Krispies, then oatmeal, and then Wheaties. The third person comes in, right, and they first see Wheaties, then oatmeal, and then Rice Krispies, and so forth. Right, so overall, with a large number of subjects, right, this should balance itself out, right? But like I said, you really can only do this if you have either 2 conditions or 3 conditions because, right, as your number of conditions grows, right, it just gets impossible to keep track of all the orders. So even if you have 4 conditions, right, so you have 4 factorial is 24, right, you would have to have 24 orders and then that times 10, so you needed at least 240 subjects, which gets out of hand quickly. So it's not always possible or practical to do complete counterbalancing. So if you actually have too many conditions to really be able to do complete counterbalancing, you have to come up with another solution to this problem. So instead of actually doing complete counterbalancing where every order is accounted for, you do partial counterbalancing, and this is also referred to as Latin square design. So you just basically do a partial counterbalance where you have, you try to do the different permutations, such as in the example right here. So you would have A, B, C, D, D, A, B, C, C, D, A, B, B, C, D, A. So you're varying it up, but you're not accounting for every possible order. So you're not accounting for all 24 orders. So in this example, you may have only 4 orders, but you're still mixing things up. And the idea is that even if you're not doing a complete counterbalance, on average, right, you should come out about roughly the same. So, right, in this example, it does come out about roughly the same. So this is actually a really good way to handle these order and practice effects. This is actually something that I use in my research, right? I don't do a complete counterbalance. I do a partial counterbalance, a Latin square design, and it works really well because things balance themselves out. Each person sees every condition, so it's a repeated measures design, but they don't all see them in the same order, which is okay because it tends to equal itself out over time. Okay, another way that you could actually handle some of those concerns that we mentioned earlier, right? If you really would like to do a paired design, right, where you're using the same subjects, but for some reason it's not possible, there's actually other ways that you can handle this. So let's say that you're doing a task that actually relies on a cognitive test. So I do research on reading comprehension. People have different reading skill. If that really is important for the study that I'm doing, I might decide to actually, before they come into the lab, give them a reading test to assess their reading skill. And then I could actually pair people up depending on their reading skill. And I could pick two people that have about roughly the same reading ability, so the same reading comprehension skill, and put one in one condition and the other in the other condition. So basically, the goal of the matched pair design is that you're, instead of randomly assigning people to different conditions and hoping that based on random assignment and the law of large numbers that you end up with equal groups, you actually make sure that you're ending up with similar groups. So whatever the measure is that you're interested in, right, in my case it's reading comprehension skill, but it might be something else. It might be you want to have an equal amount of males and females, right, in your study, or outgoing versus or extroverts versus introverts, right? You might actually control for that by testing them and then assigning them to groups accordingly. This is especially important if you have a fairly small n, because right, random assignment really only works out if you have a very large n, and that's not always the case. Otherwise, it's a good idea to actually match people on a characteristic that would be important for your study. To give you an example, right, where this is really, really important is maybe for studying different drugs. So the earlier research on many drugs that we, still have on the market today, it was all done with males, and it was mostly done with white males, right, middle class men. The problem with that is that, right, biologically, males and females are not exactly the same. So why would we think that they actually react to drugs the same way? And this has actually been a problem before, right? As we know, symptoms, for instance, for a heart attack are different for males compared to females. So initially, actually, it was, a lot of times overlooked in females because people just knew the signs for males having heart attacks. So it was overlooked. So now research is a little bit more sensitive to that. So they actually make sure that they have a well represented sample. So in this example here, take for instance, you want to test how effective a flu vaccine is. You should match your participants based on gender and, for instance, age. So in this case, right, you have one group that gets the placebo. So they basically just get a shot, but maybe there was a saline solution in there, but no actual vaccine. And then you have, of course, the experimental condition where people really get the vaccine. So to make sure that this works equally well for different genders and also different age groups, you might decide to actually do something like this. And I should say, actually, it's not gender, it's actually sex, right? Because it's biologically different how people would react to these drugs. So here you actually have different pairs. So you recruit your participants and then you ask them about their age and their sex. So in this case, right, we're pairing up this 20-year-old female, and we randomly assign one of the 20-year-old females to the placebo group and one to the actual experimental group. Then we have, a middle-aged male, right, 55 years old. One goes in the placebo, one is randomly assigned to the experimental group, and so forth. So then when you're conducting your study, you can be confident that you can actually tease out if it actually works equally well for both sexes, and also if there's maybe any age differences, right? It might really work well for younger individuals or older individuals, but if you actually match your participants, you're accounting for those differences, which is, of course, really important. All right, this is it for right now, talking about repeated measures designs and some alternatives if maybe you need to make sure that you're avoiding practice effects or fatigue effects, or if a repeated measures design is not possible, you could do the matched pairs design.